A zero-knowledge proof basically allows proving that some statement is true without revealing anything beyond the mere truth of that statement. And because of this nice property of zero-knowledge proofs, they've found many applications, as you all know, in the blockchain space, for example, in privacy-preserving financial transactions, ZK rollups, which are scalable layer 2 blockchain solutions, secure online voting, as well as many other application domains. But let's say you are a developer and you would like to incorporate a zero-knowledge proof into your application. How do you go about doing that? Typically, zero-knowledge proofs are implemented using these arithmetic circuits. So as you can see, so you basically have some inputs, you have these gates, addition and multiplication, and the circuit has some outputs. But the important thing here is that addition and multiplication happens in some modulo, some prime number, so you can essentially think of ZK circuits, as far as this talk is concerned, as a system of finite field equations. I'm going to represent the input variables of the circuit using X and the output variables Y. And in general, as you probably know, circuits also have some intermediate variables, but just to simplify things, I'm just going to write a circuit as C of XY and kind of brush the intermediate variables under the rug to simplify things. Now, zero-knowledge circuits are very common, and there have emerged many different domain-specific languages that facilitate the implementation of zero-knowledge circuits. So there are a bunch of languages. In this talk, I'll primarily focus on Circom because a lot of our work has focused on Circom, but there are a variety of other languages like NARC from Consensus, Halo 2, and a variety of others. So now from the developer's perspective, here is how the general workflow occurs if you are trying to incorporate zero-knowledge proofs into your application. So first you pick your favorite domain-specific language and you implement the ZK circuit in your DSL of choice. And then at that point, the DSL compiler will do a lot of the heavy lifting. It takes this high-level circuit description and it compiles it down to some low-level constraint representation. So for example, R1CS or Plonk and so on. And then after that point, that's where all the kind of the crypto magic happens. And then for what I refer to as a crypto compiler, this is not the main topic of this talk. But for the purposes of this talk, all we need to know is that after this low-level constraint, we basically get a prover and the verifier. And basically, the prover takes your secret information and it will generate a proof of the statement that you would like to establish. And then you can provide that proof to the verifier, which will either say, yes, this is a valid proof, or no, this proof looks invalid. Okay, so that's the general workflow we have in mind.